The following audio recording has been designed for learning purposes only. Do not share, distribute, or provide any type of copies, or this audio lesson will not be made available to you. Good luck with today's lesson.
So if there's a decrease in entropy, then the reaction would be two or more molecules coming together into one. Here we lose moles of gases, and here if we flip those around. But we'll just take it from the point of increase in entropy. All right, so as examples, so we have, so the phases will be important here. You're looking at that. So you have glucose is changed into ethanol and CO2. Do you expect that to be more chaotic or less? You think delta? In other words, should delta S be positive or negative?
Positive.
Yeah, you're going from a lot of things. First, you're going from one molecule to four. Then you also have gases. This was a solid, so everything's becoming more entropic. So this is going to be delta S is greater than 0. So can't say what the number is. We're going to calculate that later, but we can certainly say it's greater than 0. Here's how one of the ways your body gets rid of excess nitrogen. With your amino acids, you use everything, they use parts of the amino acids for proteins, and you can even use it as part of metabolism, but we always have excess nitrogen, and our bodies don't know what to do with it. So the nitrogen, in one form or another, is connected with CO2 to form urea, which is excreted in the urine, hence the name. So is this an increase or decrease? So delta S, do you expect to be positive or negative here? Yes, negative. In this case, this is not what's happening in the body. This would be all aqueous. But gases, 3 gases changed to a solution and a liquid. So definitely going for more chaotic. And there's 3 of them here down to 2. So that should be negative. All right, and then how about this one? Yeah, I mean, there's going to be, but it'll be slight. It'll either be slightly positive or slightly negative. It's hard to say here. My guess is that it would be slightly negative, because this is now you have hydrogen, which is a very stable molecule, but it would be very slight. So all we can say is that it's approximately 0. There's nothing to go on there. We have the same number of molecules. We have the same phase. They're all gases, so we can't really say anything. Or you could even say, don't know, we need more information. Yeah.
So we'll be able to do this how just looking at the whole industrial?
Yeah, just looking at the compound, the components, how many there are, like breaking down. Even if this had been a liquid somehow, it would still be positive, because it'd be 1 molecule to 3, that kind of thing. So use those rules. And then one that's the phase diagram. So if you have water that's in the liquid phase and it freezes, liquid to solid, what do you think that's going to be, positive or negative? Negative. Yeah. So it's becoming less entropic, less chaotic, so because it's going from a liquid, which is not moving around very fast, but when you get into a solid, that's ice, it's just sitting there. So definitely it is lower. How we're going to calculate it here, probably next, is we're going to take the absolute entropies of this side minus the absolute entropies of this side. So we're going to sum them up and find them. And then if we do these out, we can determine the actual number. But if we determine the actual number for this one, it would be positive. This one, it would be negative. We just can't say how far. Okay, but might not be able to do those ones because we don't have might have the numbers, I don't know. Liquid. No, we don't. Okay, so we'll have to come up with one. All right, so just qualitatively be able to do that. But then now we want to be able to quantify this. We want to be able to give a number to these reactions. And we use, remember from chapter 6, I'm sure you've gone back many times to Prue's chapter 6. So yeah, every weekend, yeah. Me too, can't help it. It was just a fantastic chapter. But this is what we did in 1170 was thermochemistry, and this is thermodynamics. So thermochemistry was just concerned with delta H. Now we're concerned with delta S and with delta G. So what you have is the heat of formation of the products. Oops. Just as a reminder. And then the entropy and the free energy all work about the same way. So what you do is you take the heat of formation of the products multiplied by their coefficients, and you sum that up. And then you do the heats of reactants times their coefficients, so whatever's out front here, sum them up and then subtract them, and that was the heat of reaction. So we'll be doing that in a bit, but let's do out one for the entropy, and it works this way. You can see that all we need is the absolute entropies of each product multiplied by their coefficients, sum up the right side, do the same thing to the left side, and then subtract them. And then the last, and I'll put up delta H here just so you can compare them easier. So it's a lengthy equation, but really it's very simple to do. And then delta G we're going to do as well. And these are all going to be at standard temperature and pressure, so we're going to use the degree signs. And then we're going to do that for the free energy as well. So you can see that it all looks the same. If we went into the tables, each of these are just sets of numbers. We're going to put them in the same way for each one that we do. So let's do out one here. Put the guy in the end here. All right. Okay. Alrighty, so we have this. Got this guy here, and I want to know the heat of reaction. You can write it like this. And I want to know the change in entropy for the reaction. And so I have to give you the data. So on the exam, it would be right in the problem. So it would be something along this line. Probably won't tabulate this way, but it'll be listed. So what's the heat of formation for nitrogen? Remember? We're forming a compound from its elements. So we're forming this element from its elements. So what should delta H be? 0. Yeah. How much energy does it take to form an element from itself? Nothing. So anytime it's in elemental form, it's 0. So on the exam, I'm not even going to put those on there. Delta H I'm not going to put on there. So if you come up during the exam and say, what's the heat of formation for nitrogen? I'm going to say, you have all the information you need. And usually what happens, they go, thanks, Dr. Z. Storm back to their table and say, but I've told you. So if you do that, you're going to... or you come up, that's what I'm going to have to tell you, but I just told you what it is. Okay, so, and that has happened numerous times. But then the student sits down and all of a sudden you're like they just got electrocuted and it's like, that's right. I was actually doing everything I could. Okay, so the entropy. It's never zero except at 0 degrees Kelvin, or 0 Kelvin. And we're at standard state. We're at 25 degrees Celsius, so all of these will have to be non-zero. So we'll say 192, and then 131. And this is going to be, this is joules per kmol. Joules per kmol. And then this is 192.7, well, let's just make 193. Kmol, joules per kmol. Okay, so we're going to find that. And then we're going to be able to find delta G as well. There's two ways to approach delta G. Okay, so if we do this out, then it's going to be 2 moles of this times minus 45.9 kilojoules per mole. And that's the product side. That's all we got there. Minus, this one's easy, but I'll just do it out completely. 0 moles times, or I should say 1 mole. 1 mole times 0 kilojoules per mole. Plus 3 moles times 0 kilojoules per mole. And you certainly don't have to do this on the exam. If you leave that off, I'll understand that you knew these were 0, but I just wanted to show the full thing here. So this is, and you can put the reaction like I did there if you want this. Make sure everybody understands what that delta H is about. It's the heat of reaction. Okay, so these are 0. So 2 times 45 point. So this is minus 91.8 kilojoules. That's for delta H. So this is an exothermic reaction. Now for delta S, this one's going to be more involved because none of these are 0. So but we do it out the same way. It looks very similar. So this is 2 moles, 193 joules per kmol. Big thing here is notice this is kilojoules and this is joules. And we're going to use a new equation to show the relationship between these two and delta G in a bit. And so these are going to, when we compare these, we'll have to make one or the other, this joules or this kilojoules. But for now, they're just on their own. 1 mole. Notice that the entropy, these absolute entropies are always positive because the lowest they can be is 0. There is an exception to that. We have ions that are in solution. They'll gather so much water around them that they'll actually create kind of a weird little crystal where it's negative entropy, but that rarely comes up. Nothing to worry about there. They're always going to be positive. I just mentioned that in case you look through the table and you do see a negative entropy. It can happen, but very rare, and nothing that we're normally going to see. So this would be 386 joules per K minus, and this is why you want to do all of this together and then subtract. Make sure you get this all, that's why I put it in the square brackets. Students will make the mistake of this minus this plus this, and then you're going to be way off. You want to do this all together, get one term minus that. So 192, whoops, 3 times 193 plus 192. And if you do this out without the square brackets, you're not paying attention, and you do it this minus this plus this, you're going to see you're going to be way off. So make sure you sum each side first before you do this final difference. So 386 minus 771. Man, that is really on the money, isn't it? I made a mistake. What did I miss here? Yeah.
The addition.
This is 131. Sorry. But man, these numbers really count. I was just taking them out of the book. I didn't notice. Yeah, so. But I did notice when we got done, we have almost the same exact number. That didn't seem, I mean, it's possible, but it didn't seem very likely. Okay, so, yeah, that seems a little bit better. So, yeah, just make sure. So I did that on purpose so you can see what can happen if you're not paying attention. Of course, on the exam, you're not writing on the wall, so you won't have as much trouble. Yeah, so that's delta S. All right, so we'll leave this up here. I think we have the delta G for this. Maybe we do. Do we have everything we need? Okay. And let me just see. Okay, so let me just double check if we have delta G here for ammonia. Oops. Okay, so now at the beginning, the engineers that were building engines, they're trying to take trains across country, make sure that they're not taking too much fuel and not enough. They want to know the efficiency of an engine. In other words, what's the maximum amount of work that can be done? Well, J. Willard Gibbs determined what should be done. And he found that, well, what was known already was that if you take delta H minus T delta S, this was known, if it's less than 0, the reaction is spontaneous. And only spontaneous things happen, so this reaction goes as written. If this is true, the reaction is non-spontaneous, and it doesn't happen. Or you can think of it, you have the reaction backwards. If you want it to run, just flip it around. But this was known. But then J. Willard Gibbs did something very clever. He said delta G is equal to this, and thus, if delta G is less than 0, the reaction is spontaneous. So he just added a term. He didn't call it G. Somebody else did later, but he had a different term for it. If delta G is greater than 0, the reaction is non-spontaneous. Well, this was already known. All he did was put a delta G in front of it. I thought, that's easy enough. I could do this. And I've really wanted to do this. I was hoping to do this in grad school. It's a champagne glass. It's a delta champagne. And just do this and then set that up and say, boom. That's all he did. He put some other term there. But there's more than that. Why could he get away with it? This was already known. So all he did was then take what was already known and give it a new name. The reason he was able to do that is because he called this the free energy. And it was something that people knew that this was true about reactions, but they didn't understand something about it. This free energy this is the maximum work that can be done by a system. In this case, a reaction. So delta G, the free energy, is the maximum work. So J. Willard Gibbs answered the question that was originally posed, probably at that time, probably at 60 or 70 years earlier. What's the maximum amount? So we have this engine. It's designed this way. Here's the fuel we're using. How much work can it do with the amount of fuel that we have? And that wasn't known. They did know that if you had the reaction set up this way, that it was spontaneous, it would run. And J. Willard Gibbs said, no, not only is that, but this tells us how much work this engine can do with this amount of fuel. So he answered the question. So that's why it's okay that he did that. He didn't just add on the letter from his name and go for it and try to talk people into putting it into the books. It's in there forever because it's so important. So make sure you know this is really important that you know this. The free energy, the change in free energy is the maximum work that can be done. So that was, and with all the stuff that was done with thermodynamics over the course of a century to get it into the form, that was the original question. Okay. Now, So, since we know this, where did I put it? Oops. So if we have that, and since we found these, we can find delta G for this as well. So delta G for this reaction, I'll do it over here. So we put in our values. Minus, so the signs are very important here, because we have a negative sign here. And if this is negative, then the whole thing will be positive, so we got to be careful. We're at standard temperature. What's the standard temperature in thermodynamics? 25 degrees Celsius, 1 molar and 1 atmosphere. These are standard conditions. So thermodynamic standard conditions. That's right, I didn't cover this before. We just got done with this in 1170. We're in chapter 6. That's what you learned. So same thing, same as before. The standard conditions are 25 degrees Celsius, 1 atmosphere, and if it's a solution, 1 molar. All right, so that we have the temperature here. So unless otherwise specified, this is going to be 298 Kelvin. Always have to change the Kelvin. And then we put in our value here. It's minus 199 J per K. And I'll just put that like that. Looking at the reaction, does this make sense that this is negative? We went from 4 moles of gas down to 2 moles. Yeah, we should have lost entropy, should have lost the chaos of the system. We have 4 moles of gases, now we're down to 2, so this should be negative. If this had been positive, there's something wrong. So in this case, that turned out right. Okay, now before we continue on, we want delta G. Delta G is usually given in kilojoules, but what do we have to do here? Let's look at the units of measure here. This term, when we multiply, it's joules per Kelvin, so that's going to give us joules. But we have kilojoules here. If you make that mistake, you're going to be way, way off. So what do we have to do to this guy? Yeah. Well, you can do one of two things. You can multiply this by 1,000 to get joules, or you can divide this by 1,000 to get kilojoules. I always do joules. I don't know. It's just how it's. I got into that habit. It's up to you. Either way will work. And it's actually better or faster to divide this by 1,000 and make this kilojoules, because you'll want your answer to be in kilojoules anyway. But I'm going to change it to this because just out of habit. And since I've done it for that way so long, I can see this a lot better. I can kind of guesstimate where we're going better than changing this to kilojoules. Does make sense. This is negative. Negative, that's why the signs are so important. Don't forget this sign. Don't think that this is positive, or you can be way, way off. So this is going to be minus 91,800 joules plus 59,302 joules. So this is going to come up to be minus 32.5 kilojoules when we convert back. So on the exam, I'm going to want you to find delta G. It's most likely I'm going to give you this data, because then you have to do it the long way. You have to find delta H, delta S, and then put it in there. But we can also do it with the data for delta G, and as a double check. So if you're on the exam, it's highly unlikely I'll give you the delta G data, but I'm going to ask for delta G, which means you do this, and then you have to do that part. But I could also give you the delta G data, which is another way of solving it. So for these should be 0. Let me double check. 0 for delta G, and hydrogen should be 0. Yeah. Generally speaking, if delta H is 0, delta G is going to be 0 for these, because it's just the free energy of formation from elements, so it should be the same. But always a little surprise on different things. So this is 16.4 kilojoules per mole. So this would be a separate problem, but since it's the same reaction, delta G is going to be the summation of M delta G of formation of products minus N, the coefficient, times delta G of reactants. And what we would find is that we have 2 moles times minus 16.4 kilojoules per mole minus 0, oops, doing that, 1 mole times 0 plus 3 moles times 0. And so this comes out to be minus 32.8 kilojoules. These should be exactly the same. The reason they're not is that I rounded. These should have been. I think this was. I'm not sure. It was like 191.8 or something like that. So that threw it off. But even the tabulated data can be off slightly. This really, in the end, is less than. It's about 1% off. So I would guess that is correct. Both of those answers are correct. Okay. So be prepared on the exam to do out this form of it. And then once you have delta H and delta S, what I'll be actually asking for the exam is for you to find delta G. So you'll have to do that in a second. You'll have to combine them. Okay. But there is a shortcut if you're given the free energy data, which is unlikely. Want you to build some character on the exams. Got to be rough, but it's just a little extra thing. But if you can do that for one problem, then you know all of that information. If you can get here with just the 2 lines there, you can get to this point, you know everything. Okay, so know that delta G is maximum work. It's not too much more to be said about that, but really, in the end, I mean, this is unbelievably important because this was the original question. And it was Gibbs that finally noticed the answer to it. Okay, what else do we got here? Oh, look at that. Our free energy and work related. If you write that, that's all you have to write. We did that. Okay. Right. Now, so a few little calculations here. We'll get rid of this stuff. It's definitely much more leisurely than going through 16 and 17, where sometimes it just felt like so no matter how fast we went, it was not enough time. Chapter 18 is one of the more easygoing ones. I think we'll do one of the problems in chapter 19 before we finish, and then I'll do the lab work. It's a redox balancing one. It's kind of fun, but it does take a long time. I think we have time to do that today, and then we'll call it quits. All right. So here's some equations you should be able to go back and forth with. Yeah, no, I guess we got that. We got that covered. All right, so we have this. So there's a relationship between thermodynamic data and the K value, the equilibrium constant. So this is a relationship between thermodynamics and chemical kinetics. So we have that set up. And in this case, R, you need to know, is 8.31 joules per kmol. This is the gas constant, but it's just a different form of it. Should make that point. This is from the ideal gas law. And this is the one that we use here. But they are the same. They are the same constant, just different units, so different numbers. That's just like 1 meter is 100 centimeters. We changed the units of measure, so we changed the number. Different units of measure, same number, but you can see that joules is equal to liters times atmospheres. But we're using this one. And we're using it because if we use this one, we would certainly get a number, but we'd have all kinds of weird units of measure at the end. We want energy. As an aside there. Okay. And we have this as the standard, so the temperature is going to be 298. On the exam, I probably did for the answer of the exam. Yeah, at the top of the exam guide, assume the temperature for all problems is 25 degrees Celsius unless otherwise specified. Yeah, so you can, that way I don't have to keep putting 25 degrees Celsius for everything. Okay, so let's look back at like KSP for AgCl is equal to, I think it's 1.7 times 10 to the minus 10. Something along that line. It's 10 to the minus 10 anyway. I might even do that one because it's a nice one. What is it here? Oh, they say 1.8, so we'll go with that. All right. So 1.8, so that's the KSP for AgCl. And so what is delta G for this reaction? Here's our KSP reaction for silver chloride. So we know the KSP for that is that number. So what's delta G? So we solve it this way. 8.31 joules per kmol. Temperature is 298. And then we have the natural log of, that's why this really small number is really leveled out by that natural log. Just becomes a fairly small, or fairly number that's close to 1, rather than being insanely small like that. Okay, and then we got to keep track of this negative here. And this is less than 1, so it's going to be negative as well. So 1.8 times 10 to the minus 10, not log, natural log. So this is, I'm going to do it out completely here. Keep some extra digits there. And this has no units of measure in the argument of the natural log, and your answer has no units of measure, so that's good. We see that K cancels, and then we're left with joules per mole, which would be changed to kilojoules per mole, so that's correct. What's the sign of G here? Is it positive or negative? It's going to be positive. And that's non-spontaneous. And we know that this reaction hardly goes to this side at all because this K value is so small. So there's a relationship between the values of KSP and delta G that we'll see in a second. So 22.438 times 298 times 8.31. And this comes up to be 55,565 joules per mole. And that's going to be 55.6 kilojoules per mole. And to make a point of it, we'll make that positive. Okay. So what we see is that if K is less than 1, then delta G is going to be greater than 0. If K is greater than 1, then delta G is going to be less than 0. So non-spontaneous, spontaneous. We haven't thought of K in those terms, but that's how they're related. So K is greater than, the larger K is, larger K is than 1, the more spontaneous it becomes. The less it is compared to 1, the more non-spontaneous. Okay, let's go with the other route. Okay. Oops. Where's the K values here? Okay, let's do out. Okay. If I can find the values. Okay. So what would be positive? So CO2. If I can find all of these on this paper here. Okay, so here's a combustion reaction. Make sure the matches up. Okay, and then we have delta G. So when you have to look in these tables, be careful. Water can be liquid or gas. Gas here is minus 229 kilojoules per mole. Water liquid is minus 237 kilojoules per mole. Not a huge difference here. That was more than that. No. But, for delta H, I think it is. But yeah, definitely enough that you probably, if you use this one for your homework, it'll be beyond the 5% grace period or grace area they give you for the problem, and that's why you'll get it wrong. This is 0, and then methane. Where's methane? Here we go. Okay, minus 50.8. Okay, so I give you this information, and then what I want to know is, what is K? So you'll use those values to find delta G, and then you'll plug delta G into that, and we're assuming it's at 298 Kelvin. So give that a try. Should be able to use these to find delta G, and that's going into this expression, and then you're going to find K. Now, I picked delta G. I have a feeling this delta G is so large that when you try to find the antifunction of natural log, that's e to the x, you won't be able to find it on your calculator. That's okay. I'll show you what you can do there. That would be the point of it. So give that a go, because that's about as tough as it would get on the exam, where I'd give you this. This would be a way of reducing down the problems, because if you can do this, or if I gave you delta H and delta S data, you find delta G and solve that, that would be everything in one go. That doesn't sound like me, but it's certainly a possibility, and homework might have something like that too. Okay. And then, so we'll do this one, then we'll take a break, and then we'll finish up 18. We'll just do one thing for chapter 19, so I'll run back and get that. It's a really long problem. It takes about 20 minutes, but it's one problem on the exam, and as fun as it can be, and it's a blast, we should get that out of the way so we can focus on the rest of chapter 19 starting next Monday. And then we'll do the lab. Okay, so for this, I'm going to do it over here. Delta G that we're trying to find, that's going to be 1 mole of the CO2. We'll do the products. Minus 394 plus 2 moles times minus 229. Right? And then 1 mole thought it was going to be positive there for a second. Yeah. So everything's here. Let me get back here. 1 mole. Yep, everything's there. So I'll do this one fairly quickly. Times 2 plus 394. So this is minus 852 kilojoules. And I make sure you put the moles in. That's how they're canceling, and you're just left with joules. And then over here, this is plus 50.8 kilojoules. So close to 800. So this comes up to be minus 801 kilojoules. Okay, so that's a very exothermic reaction, very spontaneous. Spontaneous, it is exothermic too, but from what we can see here, it's definitely very spontaneous. And we put that into our value here. So we have delta G minus, so this is a problem that I've set this one up so that there will be a problem. So this is minus that, minus 8.31 joules. And you can have per mole here if you want, like they have here. This is per K mole. 298 Kelvin, and then the natural log of K. So you can see everything cancels. That per mole depends on if you're dealing with 1 mole. And even if you're dealing with 1 mole, you can leave it off like I did. So the mole just tells you, oh yeah, we're dealing with one mole at a time. But so sometimes you'll see it, this says delta G as kilojoules per mole or just says kilojoules. Just depends on the system and what you're interested in. Okay, so we have, so you see the signs cancel. Then we have 801,000 divided by 8.31 divided by 298. So we have 323. So rearrange it here. Natural log of k is equal to 323. So let's make sure e to the ln of x is equal to what? X. So this is the antifunction of this one. So if we take e raised to this side is equal to e raised to this side. So k is equal to e to the 323. Put that into the calculator. And our answer is, that's a funny number. There we are. There's your number. I'm not sure if that has the right sig figs or not. Okay, so our calculator can't do this. That's okay. So if that's what happens on the exam, that's the number. That is a perfectly reasonable number. It's just that we like to go back to, to numbers that we see. So, but that we know. But this is, if this is your answer, perfectly reasonable. On the exam, I try to keep away from that. But if come on up, and I'm not going to tell you if you're right or not, but I might say, yeah, I didn't do that. So, but in this case, it's just too large for our calculator. Anything where I think it's e to the, for e, I think you can go. Let's see how far you can go for e. Yeah. So 300, 250, 220. Or this will take about 20 minutes here. Oh, there we go. 231. So e to the 231. Anything above that, it won't work out. And 10 to the 99th won't work out either for log base 10. So the reason I did this one, because I knew it would be too large, but that is the answer. That's e to the 323. That's a number. That's certainly fine. We just like to have it in a number we're more familiar with. So if you ended up with, if instead, so this would be another problem. So if e is minus 30, let's say 35.3, so it'll be, in the end, you have natural log of k is that, then it's going to be k is equal to e to the minus 353, and then it's something that you can do, get back to where you were, into numbers that we're familiar with. So if it's low enough, you'll get back to a regular number. But this certainly is an answer. Nothing wrong with that answer. I just want to point that out in case you come across that in a problem where it's just such a gigantic number your calculator can't handle it. It certainly has a number that like this. It's just something that your calculator can't handle. Okay, let's see. So we got one more part here, but let's take a little bit over a 10-minute break. I got to run back to my office to get the Chapter 19 stuff. So we'll start about 5 after. Well, come on up if you have any questions before I go. Okay. Oh, yeah. Okay, got it. Oh, yeah.
There's no stapler here. We'll have to take around 2 sides. Is that okay?
Yep.
And I gave Rose like
Yeah, you're kind of eyeballing it, but that's, it's very close. That's fine.
Yeah. You got a stapler?
No, I don't.
Not.
Sometimes they do. I don't see one here.
That's fine.
All right.
I have a question.
Yeah.
For this step, you know how to equal 0. So for on the exam, would you want us to show all the...
No, you can just leave it off. I'll know.
Okay.
Yeah. If you want to put it on there and just cross it out, you can do that as well.
That's
Yeah, just do it as close as you can. I mean, if you have a ruler, that'll make it closer, but
Because some of
yeah.
them we didn't need to do the calculation, like for the HCL.
For the first
I
one
just did
and
it on
fourth
the
one.
ground.
Oh yeah, they didn't have one that we weren't interested in a K or KA or KB. So yeah. So yeah, for that one, you just have to say where you think the equivalence point was. So what I'll do is I'll take your numbers, I'll look at it and see if it's close. You can probably see much better than I can. So yeah, so I'll take their word for it. It's right there. Okay, so give me a second here. Run over to the office and do something with this. Oh yeah, you don't have to staple it. Just write your name on each.
That doesn't matter.
I just take $5,000. Oh my God, really? Bro, that's good. I'll do it. That's 30.
Oh, wow.
This is crazy. A flight from Detroit to San Diego is Is that round trip?
I'm not trying for Michigan to do the test, like the amount of time like I wasted for it. Like it took me 2 hours only to get some information from here because I had to go there. I couldn't find it online, and they said to me it took me 2 hours and then 4 hours the whole day. I was there. When I came back, I was like, no way. I'm not gonna try it here.
Sarah wanna come? She's saying no. I don't know. I don't wanna go because I wanna come back and do it. Because I haven't done anything.
So that's why I'm saying, like, just quickly.
Either the 230 mile one.
I don't know.
Dude,
I want
you
to
know
know.
what she's looking at the tuner table.
Let's say I wanna come back March 3rd.
You're gonna have Corona tomorrow.
No, I'll have 2 on it. Spread it because I'm not going to.
Oh my God.
Thank you.
Bro,
Thank you so much.
Oh yeah, sure you would. Yes, sure. Okay. I'm not even a German. I'll fix you up before you.
really, I'll leave tomorrow.
Not in a public school.
And I get to that? It won't. Still.
You're joking. Oh my God. All right.
It was funny because I actually had a call. I saw you go.
Team will fight for the school.
Whatever this coughing is.
Right?
We need the 5 calculation for the school.
Sorry, buddy.
I'm not even
San Diego?
That's a good idea. Just to take pictures. I didn't even concentrate in the class. I didn't even know what was going on.
Can you not say Chipotle?
They said they'll have the decision by mid-April. Which is fucking garbage. Yeah. Maybe I just said a little. Or no.
Probably my aunt was there. Oh my gosh.
Decision I got the
Because I've been
first
sitting
time.
on the decision forever, I just haven't done anything with it.
I think I applied in December for like before.
Yeah,
earlier.
but they were my best offer.
Well, earlier actually was like November.
November 1st was the
And mine was either.
There's two new.
I think it was early December, or late November.
One of my friends that applied to LSA applied June 3rd, heard that week later. And then again, she also got 4 right in it.
Well, I wish I was that smart.
You're just poor.
Ew, I literally hate my voice.
Did you say that?
Yeah, I know.
Okay.
She's like, can you turn your lights off? Look, you're for my birthday.
They're supposed to on
Yeah. Dude, I was looking at my Oakland. Yeah. Alright, first of all, like, my family makes a decent amount, but that's still a steep amount of
Yeah.
Oh my gosh.
Yeah.
Oh my
I
god.
expect them to cover all of it. That's a lot of money as a semester.
Probably like $50 good for it.
Okay, like I would die.
You can probably get first
They gave me like 5,000.
for what?
Let's see Luke again. What's the cheapest airline in this year?
Oh no.
I think he was looking at Spirit.
Spirit's the worst one.
Yeah, but it's cheap.
There's like holes in the floor in Spirit.
I went all
But
the
the
way
plane's flying. That's what
in Spirit.
I'm
He landed
Where do we
and
go?
smashed on the road.
Is this the place you went to?
Yeah.
Are they good?
It's just like your airplane is not
My god. For Euro fries and a drink.
Yeah, I know it's like
You have
weird.
multi-billion-dollar
It's
city
$50.
How it works for everyone.
20 euros and
No,
It's in New York, it's probably way cheaper.
It's just holes and like this thing.
Where are you?
If you get the combo, I think it's
Combination.
What?
Honestly, I think I'd rather do that.
It gets cheaper the further out you go. You get $56 if you go on Wednesday, March 18th.
it's just so cheap.
$37? We can get like $20
Flight to New York for $20 like a Wednesday, March 18th.
Sarah's having a rough
So
time.
we get one person to go. I bring 5 somethings. You know, stuff and shit.
That's like the price of a train ticket.
That's cheaper than the train.
Literally, what is it?
Is hand sanitizer really $20?
And it's a sanitizer.
Everything is
You just not go to the
Sanitizer.
No, I have
go out like a couple months. Everything is cheap as fuck.
Someone came and bought like 8 of them.
Dude, New York.
I could travel the world on the coronavirus money.
We get 15 different kinds of.
Go to New York, and go to somewhere in Europe, drive over to Europe, and then go to Russia. Come down to Australia.
$40, all right.
Australia's probably has a flight to Russia, right? I'm like,
No, you probably go from like, say, LA or something.
yeah.
Because he was going to do
You
it.
probably don't go.
Oh my God, stop.
Yeah,
What airlines go to
that's
Russia?
easy to do.
If you go to this, I'm gonna go about it.
I'm just trying to figure out.
You want to know?
Yeah. We can go to the no, but you can
Well, I said Chipotle.
You probably don't travel. You go to Russia. You go to Russia.
I got it.
Where should we go to?
Must be nice to have some. Must be nice.
For more.
And this is why I have
This land. I was so done. The gulag's on the west side.
I'm gonna go with the lines.
That's really never come.
I mean, would you get it?
Yeah.
Okay, how about
I'm
April?
still
Stapler
friends.
up here?
Those planes are getting the next
I have one.
Oh, you do? Could I use it? Thank you so much.
Yeah. Check out my first letter. How much? It's probably like $50. I'm trying to I can literally get
Thank you.
They're like, no, we're not. Drinking shit, thinking you're all fed.
Excuse me.
And that.
Hold on.
Purple line.
Oh my god. You think like you guys are we're gonna find a Russian club.
Dude, why do you want to go to Russia?
A Russian game. I want to see if you can go to Russia and how much it would be.
Probably like 50 below. Go to Russia. Everyone book your planes now.
Oh my god.
Oh, Central just went all online. What? Yeah. That's
These
crazy.
cases were reported like not even a day ago, and all these schools are all like shut it down right now.
One of them is in Wayne, the other one's in Oakland.
Weird sight set up.
What I don't know is they're like on the other side of the world. There's no way to get out there. The one friend who goes there is in Tennessee right now. He's probably trying all he's gonna do. He sounds great.
If I go to Russia for under
Round trip to Florida, they said the fire fuel Friday. Sarah, book your flight. What's this? 3 weeks going on. I pay for a good time, not alone.
I'll see how you'd be able to do a lab though.
Yeah, how do we get to Russia?
I'm trying to
Like
find
a flight for tonight, 6 p.m. Let's go.
Weird. The exams would be so easy.
Facts. I know, I see it. Out there, like you bring the glass.
in my head.
You can't make those kinds
I know it does that.
$69.
Ready?
You're going? You do it.
And moving classes
Yeah.
to
I get it, you get it.
virtual
Huh?
instruction
You get it? Yeah, I mean, it's life.
until
It's like
It's life.
I've never
and then they
heard
said with
It's
T,
like
work on
a
faculty and do faculty and stuff on laboratory.
You know we're about to do the first one to get into is
Oh, yes.
What?
I wait for
This semester? Yeah.
I don't even want to wait.
I'm never paying for a flight
It's honestly
over
gone.
Yeah, like
75.
It's not gonna be
I
cheap.
just have to wait for my agents to come.
I don't know if we can change it.
Whoa.
Like, if I just
The guy that
go to the park and have something, I think I'll
graduated makes it. So.
I don't care if it kills other people. Gross. I'll be fine.
Where's population? Don't usually care about people.
But like for the Michigan transcript, it's like.
Let's go.
Yeah, you have to do like 2 hours.
You're gonna order from high school.
You eventually gotta get
I was
Must
gonna
go
go
like
like
4
Where's high
It
school?
says 248, but
It's not weird.
I think it's that seems to change the one with your
It's gonna stop, so just take the
I think our ticket, I
I
think our tickets to get on the Fort Lauderdale in the beginning of February was like
I'm pretty sure Fort Lauderdale has ball cruising. Something.
Wasn't Ken was yeah, 398 is the cheapest.
Yeah, I have
Like, which yeah. Yeah, that's where a lot of them
It's gonna go. It's gonna go.
Run it up. Did you see the guy that was like licensed to like Irish music?
What?
You didn't see him? He was.
Yeah, right there.
Yeah.
Okay, he's always blasting music.
Oh, definitely.
Why
Because
do
he
you
does like dance and it's like. He's kind of mental. Not a mental problem. That's a shitty thing to do. He was just like dancing to Irish music. It was really cool. It was like stomping around. It was wild. You just not caring what people think about you and just like that's what you
I really like this part with chemistry as well.
Yeah. 8-12.
If I hate biology,
What's
I used to have
Spirit?
Now we have like that.
No,
Dude, Spirit first class is like almost easier than all the other airlines.
But like, it's like, because how did you do this? So like, you scan
oh, these two things are
It was
No, 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 that's just
yesterday.
so when you want to do
You look for a way.
Because I did it yesterday. I didn't find it can have them online.
So 200 is take a flight. Just go back there.
If it were me, I don't. I'm not gonna let you.
All right, so just we'll talk about it here because this is where it's defined, but we won't use this till chapter 19. So the thermodynamic equilibrium constant is special. It's just the constant under certain conditions. The gases are given in partial pressures, so it's like a Kp, and this the concentrations are given in m molar. So you have something like this. So at first it's going to seem like you're just making a lot of work for yourself, but then you see that we're going to be at standard conditions, so everything gets to be a lot easier. So if you have this, normally what we would have done is Kc would be this. If we did it using Kc, using concentrations, we could also use Kp, then it would just be, oh, actually we just have this. But we lose the concentration, this aqueous then would be something that we couldn't use up here. So actually we'd have to leave it like this because we wouldn't know what to call it for Kp. I guess you just say it was 1. So, but we don't normally try to split them when there's more than 2 phases here, and of course we leave liquid off here. But the thermodynamic K, this is going to be equal to the concentration of the urea over the partial pressure of ammonia times the partial pressure of CO2. So it combines these two. So I said, well, that doesn't seem like it makes things easier, but under standard conditions, what's the standard pressure under, what's the standard pressure? Or what's the pressure under standard conditions? 1. So this becomes 1 squared. The partial pressure of this should be 1. And then what's the standard concentration? Right up there, 1 molar. So 1. So under standard conditions, K always equals 1. And we're going to see later on in chapter 19 that we're going to take the log of K, log base 10. So what's the log base 10 of 1? The log for any kind of log of 1 is 0. So you do that under standard conditions, you'll take this very complex problem or equation and really simplify it. The log term is always 1. So that's why we have it. We didn't use it before because we were trying to find something that was beyond not necessarily standard conditions. We couldn't count on these all being 1. But under standard conditions and using this logic here, then everything's 1, so K is 1. So when log of K comes up in our problems in 11 or in chapter 19, which it will a lot, we just set it to 0. So it'll be some term plus some log term. The log term will always go to 0. So you should be aware of the thermodynamic equilibrium constant. I don't even think I asked you a question about it on the exam, but you should know this. We're going to see it again in chapter 19. So just to give you an idea that if we do this where we take the concentrations in molars and the gases in pressures, we get a very simple answer. So for some of these problems. Okay, so that's an aside. Or let's just let you know. We'll be seeing it. And then the last problem here on chapter 18 is qualitative in dealing with, well, I should also mention, maybe they have it here somewhere. Will they make a big deal out of it or not? Did they say anything qualitative about delta G for this one or not? Yeah, they do. Okay. So, a little qualitative aspects of delta G. So just looking at delta G, you can say something about it. You can say when delta G is a large negative number, says more negative than minus 10 kilojoules. So from minus 10 to minus 20 all the way down. When delta G is a large negative number, the reaction is spontaneous. And has mostly products. So if you did this reaction out, the more negative it is, the more the reaction shifts to the right. So if you had something that's like this, you'd expect that there'd be really no reactants to see. Okay. Then, when delta G is a large positive number, and these numbers are just picked. I mean, I'm sure there's books that use other numbers, but it gives you a basic idea. Plus 10 kilojoules or greater, the reaction is non-spontaneous and has mostly reactants, say, at equilibrium. And then, when delta G is small, between minus 10 kilojoules and plus 10 kilojoules, have measurable amounts of reactants and products. So this is one of those where the reaction only goes slightly to the right, and you are left with reactants and products. You can measure them both. They're very easy to tell they're both in there. For some of them, you might have some reactants left, but they'd be such a minuscule amount it'd be hard to tell. But here, you definitely have amounts of each. Okay, so that's actually two things. I'm kind of doing some sweep up here, but now the last thing that we need for the exam. So that's a good thing, but these are just things that are good to know. So if you see minus 400 kilojoules for delta G, you know it's spontaneous and also lies very far to the right. If it's plus 400, you know it's non-spontaneous and lies, it's like a reaction that doesn't really go. So you should be able to tell just from the number and the sign what kind of reaction you're dealing with. Okay. Now, all right. So from delta H and delta S values, we can determine how delta G changes with temperature. We're always at 298 so far, but here's where we're going to alter the temperature. And we want to know, if we know what delta H is and what delta S is it spontaneous at low temperature, non-spontaneous at high? Is it non-spontaneous at low and then spontaneous at high, or is it independent of temperature? And it depends. All four possibilities are allowed, depending on what we're dealing with. Okay. So you can have delta H is positive and delta S is positive. And that's going to mean that delta G is negative. Well, let me just do it first. We'll figure those all out here. So minus, and then what they do? Oh, shoot. Actually, I got this wrong. Fine, let's do this. I mean, we're going to do them all, but we'll put these up at the top because they will. These are the ones that don't change, and then these are temperature dependent. So I just shifted them so that we see them all in a. These two are the easiest. Okay, so if you have delta H is negative, it's exothermic, and delta S is positive, what happens to delta G? So we write this out, delta G, delta H minus T delta S. Okay, so delta H is negative, so I'm just going to write it in I'll put in a square brackets here for the sign, just to indicate we don't know what it is, but it's negative. And then this is going to be negative. What do we know about the temperature? Can it be negative? Now that's the whole point of using the absolute temperature scale. So we know that temperature is going to be, so this is the sign for this. Just put this a little larger here. This is this, so this is always positive. And then this one says in this particular instance, this is positive. Okay, so what does make this whole thing here? Yeah, whatever this number is, it's positive times this number. That'll be a positive number, but there's a negative here. So the whole thing is negative plus a negative. So it's negative. So what we're saying is that it doesn't matter what temperature is here. Even if it was 0, then it's just gone and it's negative. If it's anything positive, then the whole thing is negative. So that means negative at all temperatures. And let's do this, say spontaneous at all temperatures. Let's go with that later, but spontaneous at all temperatures. It's the best case scenario. You're assuming you want the reaction to go. So if you have an exothermic reaction that also produces a lot of chaos, a lot of entropy, then it's going to be a reaction that goes, whether you do the reaction at very low temperatures or very high temperatures, it will always go. Now, but this one, it's the reverse, so you'd expect that it'll be non-spontaneous at all temperatures. So let's do that and see. So here, delta H is positive. The temperature is always positive. We said that this is negative. These are temperature independent. Delta G is not. So these will always be the same constant number, constant sign. So what's this come out to be, no matter what these numbers are?
Positive.
It's going to be positive, so. Probably better use arrows or something, but that's fine. So it's positive, so that means that it is going to be positive. So this is going to be non-spontaneous at all temperatures. So this is the worst of all worlds. If you want a reaction to go, and you look up the reaction in the tables that list these things, and you calculate it like we've done, you find that the heat of reaction is positive, it's endothermic, and then delta S is negative, it's never going to go. There's nothing you can do with temperature. You cannot heat it up or cool it down enough to make it go. It's going to stay non-spontaneous for all temperature. Okay. Now these are the ones, the next two are temperature independent. So first we're going to determine, is it at low temperature or is it a high temperature, and that it happens, and then we're going to figure out the shift. When does it change? So let's look at this guy first. So we have delta H is minus. So we can see that this is going to be a minus, and this is going to be a positive value. The only thing that can change here is temperature. So when temperature is 0, this term is gone. So at the lowest so when you're dealing with these equations, it's always a good idea to look at the most extreme case. The most extreme case is that T is 0. I guess the other one is infinite, but here we'll start with this. If T is 0, then this term is gone. So at low temperature, at the lowest temperature possible, that's the value of delta G, or the sign of delta G. So at low temperature, is it spontaneous or non-spontaneous? Yeah, it's not. It's negative, so it's not. What's that? You said? Spontaneous. Yeah, spontaneous. So you can say negative at low T, and then it's going to be positive at high T. That's all we can say. We don't know yet when it would change. But you can see that since temperature, you can see that the temperature can rise. This term that's positive can rise. And since there's no limit on temperature, we can make it thousands, tens of thousands of degrees. Eventually, this positive term is going to get overwhelmed the negative term, and then it's going to become non-spontaneous. So it's going to be spontaneous at low temperature. It's going to be non-spontaneous at high temperature. And what do you suppose this one's going to do? And this is what I find pretty fascinating about in the sciences. You study nature, and every possibility seems to come about. Everything's possible here. So we have ones where it's always spontaneous, always non-spontaneous. Here where we have spontaneous when it's low temperature and non-spontaneous when it's high, and this is going to be flipped. We can take a look at that. Okay, so we do this out. We see this is positive. This is positive, and this is positive. So this whole thing is going to be, this is going to add, it's going to be a positive. This is a whole negative term here, so it's a positive plus a negative that is temperature dependent. So when temperature is 0, then it's going to be positive. It's going to be non-spontaneous. But then if we keep increasing the temperature, eventually, no matter what this value is, eventually this number is going to be larger and it's going to become spontaneous. So you can say it's going to be plus at low temperature. It's going to be negative at high temperature, which means it's going to be non-spontaneous at low temperature and spontaneous at high temperature. So those are all the possibilities. So you gotta, these two are the easiest, but these ones like when I'm explaining, I like to have this here before I even say it out loud, because I can kind of visualize it, but I really need to see these signs. So you want to make sure that if I ask, I say, what happens at low temperature when delta H or delta S are these? Well, it's going to be spontaneous no matter what. But most likely I'm going to choose one of these two systems, because they're a little bit more involved. All right, so one thing that we can do, though, we can determine when it changes from spontaneous to non-spontaneous, or back again. What temperature does it change? Okay, so if we have, get one here. Yeah, so a reaction has delta H, reaction is equal to, let's say it's minus 110 kilojoules per mole. We'll just say 1 kilo. Yeah. And delta S is equal to, so negative, we'll say negative 445 kilojoules. Okay. So at what temperature does it change from spontaneous to non-spontaneous? So we know from what we just did, when they're both negative, it starts out spontaneous at very low temperature. But then somewhere along the line, as the temperature rises, it eventually becomes positive. So what's the break? What's that shift? So this is talking about delta G. So delta G is negative, and then eventually becomes positive. What's that borderline then, when delta G is what? It was negative, now it's positive. What separates? Thinking back to the number line. You have the negative side of the number line. 0, and that's what it is. So there is a point where delta G is exactly 0, and if you're raising the temperature, it's going from spontaneous to non-spontaneous. If it's high temperature, it's non-spontaneous, and when it hits 0, it becomes spontaneous. So delta G, so you could say the temperature, so one of the answers would be the temperature when delta G equals 0. But that's just qualitative. We know that's true, but we can also calculate it. And on the exam, that's a very likely thing to happen. So we write it here, like this. Notice we don't put in I didn't put the degrees here. Why not? Why don't I put the degrees in? Yeah, standard temperature is 298 Kelvin, and we're saying we're all over the place. So we just have to, so this is perfectly fine. This is just in general. So this shows us we're no longer at one temperature. So we want this to be 0. What did I say? So, actually this is wrong. That should be that. One's joules per K, and then one is kilojoules. So I'm going to change this one to 100,000 joules. I'll leave off the comma just so it doesn't get too crowded, too complex. We don't know what T is. That's what we're solving for. And then this is minus 445 joules per K. Okay, so the first thing is a minus, and this is a minus, so we can just do that. Okay. And, all right. And then we have, shift this over. All right, so what I'm going to do is, so I did that. That's okay. Change the sign. And then I'm going to subtract this from both sides. And let's do it this way. So we'll have minus 445 T. That makes a little bit more sense now that we're solving for T. So that's gone. So minus is equal to, so for a second there I lost track of them. It says the temperature looked like it was going to be a negative temperature. It can't because it's Kelvin, but it's because you have to bring this over here. And could have certainly brought this over too, but, and then Line T, 110,000 divided by 445, and this is going to be joules per K. So that's going to be 1 over K, so that is kelvins. So at 100, so these could be pretty large numbers. Oh, not too bad. Actually pretty cold. Oh, look at that. So at 247 K, if we put that in, then delta G is exactly 0. So we're assuming we're warming it up. It was at really cold temperatures. Now we're getting up to, this is still pretty cold, but we're approaching room temperature. And by the time we get to room temperature, we should, here, right at this point, it's neither, and you really can't balance a reaction on that knife's edge. It's never going to be exactly 0. But you're heating it up anyway, and eventually it shifts over to being into non-spontaneous. So this is the so right there, depending on if you're heating it or cooling it, it's changing from one to the other. So something like that, certainly qualitatively you could have that over there, fill in that table or part of it, and then here you might be asked to do some calculating. And that is 18 compared to, say, chapter 16, which is a monster.
Really quick, why did it turn plus the 445?
Yeah, because it was written like this. And then I had, once I made this positive, I wanted to subtract this term off. Very awkwardly done, sorry about that. But yeah, the best thing to do would have been just to bring this over. I didn't know, I'm tired or something. I still haven't caught up with the daylight savings time. I was supposed to meet my mother-in-law for lunch on Sunday, and at noon, I thought it was 11. I said, I'm doing good. I'm going to go get the car washed. And I get this call, and it's like, that feeling, like, oh, I said, did that happen again? Do we do this every year? Anyway, but still haven't recovered. Okay, so let's do out just this one. I'll do out one example of this, because, and I don't want to jinx this here, but every class has the one topic that seems like as a class they have trouble with, and it's never the same one. This one, sometimes the students are just like, it's a breeze. Other times they're looking at me like I've just scrawled the craziest stuff on the board that doesn't make any sense. And so I want to do one of these out. But this one, it goes back and forth. Now, when we get into chapter 19, we have the balancing of redox reactions. And it can be just a really fun, really quick and semi-fun game for the students, or it can be kind of a nightmare. And we don't want that to be the case. So let's look at one here. All right. All right, so we see, let's see, we get something else here. I'll find one that, yeah. And today we'll only worry about acidic. On Monday we'll do the basic form of it, basic solution. But before we do that one, I just want to show you why these can be a little tricky, because that you can't do them by inspection. I'll put it over here. Yeah, this is a good one. Just to point out why this can be very difficult. Okay, so here's an unbalanced redox reaction. All right, so how do we balance the hydrogens? What do you put on this side? What coefficient do you put over here to get the hydrogens balanced? Okay, so we got our first problem, that hydrogens don't exist on the other side. What's the total charge on this side? This is 0. This is minus 1. So this is minus 1. Over here, we have plus 1. So the charges aren't balanced either. The charges have always been balanced for us. So what we've always done in the past is called balancing by inspection, and it's mass balance. This since we're doing redox reactions, where electrons are transferred, we also have to do charge balance. So we're going to do mass balance first, and then we're going to do charge balance. Yeah. Oh, yeah, right. Even worse, right? Yeah. Good eye. Yep. So you can see that the charges aren't balanced at all. We don't even have hydrogen on the one side. What the hell? So I had that one set up to do, because I think that one will have more to it, because the zinc, this will just be an easier one. So even though it looks tougher, it's actually going to be an easier one of this one. Okay, so what they say to do for this problem is to break it up into its half reactions, oxidation and reduction. So what they say to do is to find all the oxidation numbers, if you remember those rules. All right, so what happens to the iodine? Is it oxidized or reduced? You go from here to here. It goes from 0 to plus 5. It's oxidized. What happened to the nitrogen? Went from plus 5 to plus 4. It was reduced. Well, you can do that, but when we do it the way that we're about to do it, and then they said once you know that, then split them up into their half reactions. So the half reaction goes from here to here, that's 1, and this one to this one is the second one. Now I say you can do that, but you'll always have 2 reactants and 2 products. You're going to be splitting them into 2 reactions. So, and oxidation and reduction, we'll figure that out as we go. We're going to have to split this into 2 reactions. So we have iodine. What do you think iodine goes to? Do you think it metamorphosizes into nitrogen? It's got to go here. You got no choice. I'm going to leave out the phases for now. So that has to be one of the reactions. The other one has to be this. Now the reason we're doing this is because this will allow us to see the electrons that are transferred, which will allow us to balance by charge. Okay, so this one has a lot going for it. Okay, so first thing is split up into the half reactions. Looking at this, won't do this one out, but this would go with what? This zinc. With zinc, yeah. So this would be the half reaction. There's no doubt about it. It has to be. This one has to go, nitrogen goes with nitrogen. Even though the hydrogen is there, we're always looking at the non-hydrogen, non-oxygen elements. That's what we do first, because we have a way of balancing the hydrogen, we have a way of balancing the oxygen. But the rest of them we just have to do by inspection. So now we have it broken up into the half reactions. That's the first step. Now they say the next step is to balance by inspection anything that's not hydrogen and not oxygen. So the iodine here. There's 2 here, so what do we have to put here? 2. Just like we always did. So that one's done. Nitrogen, are these balanced? 1 and 1. Yeah, so those are done. So now we don't have to worry about them ever again. We have to worry about the hydrogen and the oxygen. Okay, so what they're basing this on is its acidic solution. So in acid solution we have water, we have H+, and for a redox reaction we have electrons. So the water is going to be used to balance the oxygens. Then the H+, that's in there aplenty, that's acidic, so there's H+, will be used to balance the hydrogens. And then we're going to balance the charge with electrons. Those are the 3 things that are in there. Okay, so looking at this, these are the 3 things we can mess with in the solution. These things here plus these 3. So balance the oxygen with water. How many waters should go on this side to balance? Don't worry about the hydrogens. We're adding hydrogens, but we'll take care of it. How many waters should be on this side? I heard 3. Don't forget that. Yeah, so 6. So definitely 3 for each of them, but there's 2 of them, so this is going to be 6 waters. By balancing with something that is definitely in an aqueous solution, we have all the oxygen, so we're set. But now we've introduced hydrogens. And it says we balance the hydrogen with the other thing that's in solution, H+. So how many H pluses do we add on the other side? 12. Yeah. Now here's where it can get alarming, is that these numbers can jump drastically depending on these charges once we get going. So you can end up with, at the end, for a multiple choice exam, they usually ask for the number of water molecules at the end of the reaction. And the number of water molecules can then be from anywhere from 0, I've seen it all the way up to like 30 or 40. So it's all over the place. Anything's possible with these. So you got to be really careful with the bookkeeping. So we check the iodines. We had 6 oxygens, 6 waters, 12 hydrogens, 12 hydrogens. So that one, as far as the mass, we've done the mass balance. Now we have to do the charge balance. What's the charge on the reactant side? What's the total? Look at the charges on each of them. No charge, so 0. How about this side? And this is where you got to be really careful, because if you're off by 1, you make one mistake on this, it can expand out, and it'll seem like the right answer, but you're going to be way off. So what's the charge here?
Plus 10.
You got plus 10. So it's plus 12, plus 1 times 12, so plus 12 minus 2, so plus 10. So if you forget about that 2, then you'll end up with plus 11, and it can go, you'll see. You might find that you end up with an answer that seems crazy, and it probably is. But a lot of times it's hard to tell. Okay, so we need to balance the charge here. We have a 0 here. We have a plus 10 here. How many electrons? Electrons are minus 1. How many electrons, and on what side do we add them? What's that?
Plus 10 electrons on the right side.
On the right side. Remember, the electrons are negatively charged. So if we do this, that's a minus 10, and this is a minus 2, so that's a minus 12, plus 12, so now we're at 0. They won't always add up to 0. You're just trying to get the charges the same on each side. If this had ended up being a minus 5, then we would have just added 7 or whatever we need to add there to make it the same charge. But in this case, they come up to be 0. So that's the other thing. That charge on the electron is negative, so you're adding negative charge, which can throw you off. But now we're done. That one's done. Now we have to see what this guy does. Nitrogen is set. How many waters and on what side?
1 water on the right.
Yeah, you have 3 oxygens. You have 2 oxygens. So we need 3 oxygens over here. We don't have them in this molecule, so we add in. We add in that. Now we've balanced the oxygen. And it's the only way we can do it. You can't just throw oxygen in there. We have to deal with what's in the solution. These are the 3 things. We're kind of hamstrung by that. That's all we can do, but luckily it's enough. What do we put? How many H pluses and where? Yeah, we have 2 hydrogens here, so we just add 2 H plus. But in doing that, we changed the charge, which, again, why you have to get the bookkeeping right. What's the charge on this side? Yeah, plus 1. What's it over here? 0. And this is unusual. Usually they aren't, there's not a 0 there, but this one works out. Everything's possible. So we now have to balance. So the mass, let me double check. The mass is balanced. Now we balance the charge. How many electrons and on what side? On the left side. Before we do anything else, even if I was hiding this, let's say I'm not going to show you, and I ask which side is the electron on? Or the electrons. How do you know it's on the left? Looking up here. Remember, we're dealing with a redox reaction. This is is this a reaction? Is this oxidation or reduction? Electrons are the product, which means they're leaving. So is this oxidation or reduction? Oxidation. Oxidation is the loss of electrons. So the electrons are the product. So we can also say that this is oxidation, which guarantees, since it's a redox reaction, guarantees whatever this turns out to be, this must be the reduction, which means the electrons have to be on this side. Once we verify that the electrons are a product on this side, where did they go? They must have gone over here. They can't both be on this side, because when we get done, we have to add them together, and the electrons have to cancel. The reason is the electrons are never in solution. They're transferred directly from species to species. So you can't have electrons just appear out of nowhere. So what did you say? What was it? How many? 1. Yeah. So yeah. put this over here. Make it this. But here's why I say don't worry about finding the oxidation and reduction. They say to do that the first step. You're free to do that, but it's kind of a waste of time because you know that it has to go like these have to be together and these have to be together. And then you balance them out, and whichever one has electrons as the products, that's the oxidation. Whichever one has them as reactants is a reduction. Okay, now here's the deal. So now we've balanced the charges. Now we have to slap them back together. Both of these are happening at the same time. We just split them apart to make it easier to see the electrons and what's going on. We have 10 electrons here. We have 1 here. So what do we have to do before we slap them back together? Those electrons can appear or disappear. They have to be the same number. So what do we do to this reaction? Not add, because it's already balanced. We don't affect anything.
Multiply everything by 10.
By 10, yeah. So it's balanced now. The mass and the charge are balanced. We could certainly put just 10 here, but then we've messed with the charge. So we don't want to do that. So if we multiply through by 10, and that's the numbers can be even larger than that. So this is 10. This becomes 20. This becomes 10, 10, and 10. And it's quite possible like that this, if you could have had the 12 down here, then you'd end up with 120 of these. They could be very large numbers. But the product electrons have to match the reactant electrons because they're the same electrons. They have to cancel. So then what we do, we add them up. And you can certainly cancel from here, but I'm just going to put them all in here so you can see everything, then cancel them below. So we have 10. Yeah, so we get oops, 20. Trying to put them where the stuff that's going to cancel will be on the outside here. So just bringing all this stuff down here. So 10, water, this, yeah, so everything's been transferred. And this 2I, okay, plus 10 NO2, plus 10 waters, plus 12H plus 10 electrons. So a lot of stuff. But first and foremost, we know this has to cancel. These always have to cancel. If they don't, you have electrons that either came into existence or disappeared, so that wouldn't make any sense. Anything else that has to be canceled? This is a good one because it cancels everything. Or everything that can cancel does. Anything else on there that you see? Appears on both sides. What's that?
The hydrogen ion?
Yeah, the H plus, there's 12 of them, and then 20 here. So this changes to 8. Anything else? And the water. So those are the 3 things that generally cancel, but except for the electrons. The electrons always have to cancel, but sometimes you don't have any waters. Sometimes you don't have any H plus, they just balance properly. So this is the end result. Let me take a look there. And then we will do out, here's the final form of it. Where's this gas up? So this is, I think, the problem is, I mean, it's very complex, but it's very procedural. We'll start with this on Monday. And you would write it as acidic. We can also balance this one in basic solution, which is all it is 2 more steps after this. But you can see that that's no easy thing. And starting with what we had up here, there's no way of knowing you're going to go from here to here. You have to break it up into its half reactions, mass balance using these, charge balance, slap them together, cancel everything that you can, and that's your answer. So, like that one over there, the reason I didn't want to do that one, because zinc, all you're going to do here when you balance this, we can do it really quick. There's no oxygens to balance, no hydrogens to balance. How many electrons on which side? So that one, no problem with that. I mean, that might be on the exam, but that's very simple. And then this one here, just do it real quick. This would be 3 waters to balance the oxygens. How many hydrogens on this side? Don't forget these. 10. And then you see this is that plus 9? And this is plus 1. So how many electrons and where? 8. Yeah. did that. And then, okay, so actually this one's not too bad. I won't go all the way through it, but what do you have to do to this one here? By 4. Okay, now let me just do this real quick. What if it had been this? What if it came out to be this? What would you multiply this by? 2, and then this by 3. So sometimes it's not as easy as some simple multiple, but it's certainly going to be that. If this was 4 and 7, you multiply this by 7, this by 4. So a lot of, anything that you can think of can happen. And if you just do a few of these that you see on the homework, you're going to find all kinds of variables. So we'll start with this on Monday. Okay, so if you're set, enjoy the day. If you want to, I'm going to work through the calculations for the lab here in a second. As I find a cough drop here, my throat is really dry. I got out of practice with the lecturing. It doesn't take long. And make sure you turn in your lab. Right, that's what's up here. Yeah. If you got that done, turn that in. Get that homework done. Fun is for the summer. No fun till then. Just chemistry fun, which is very little, very dilute. I don't think this is right. Oh, it is. Okay. Yeah. We did 3. Okay. So what I'm going to do is the one for the titration of acetic acid buffer and sodium hydroxide, and then the water one that goes along with it. Then if you want to stick around for the other ones, you can, but they work the same way. But I'll just do these 2 out. And that way, if you feel you got it from there, you're good. All right. So, where's the? All right. So, you're using your concentrations from the previous lab. Should have those. So the first calculation is to determine theoretically what your pH should be for your buffer solution. You know how much of the sodium hydroxide you put in. You turn some of the acetic acid into acetate, so you created a buffer. You know what the pH meter said. Now you're just confirming it. And usually it's fairly close. And then the other calculation is to put in sodium hydroxide in and verify what the pH should have been. You found it was going to be high, like around 11. Okay. So mine, I'm saying the pH meter so my original buffer was 4.92, so you had something along that line. So this is a buffer, and this is the acetic acid acetate. Let's dine out. Okay, so what happened was, for mine, let me just write my data here. So we had 50 mils of acetic acid. Yeah, we'll write it all the way out. Plus, I had 32 mils of, and so I had of 0.098 molar acetic acid. So everyone's going to be around 0.1. I just chose that relatively at random. Try to keep it near 0.1. And the sodium hydroxide is going to be about that too. So I made them a little different from each other. Okay, so mixing these according to my pH meter gave me 4.92. So what I want to do is use this data to verify what the pH meter said. So So you had 50 mils of the acetic acid. People have something like that for their sodium hydroxide in the 20s, 30s, something like that. So whatever you had is what you have. But this one, just kind of backtracking gave me really good results. But that's what I was more or less seeing for people. Okay, so first thing is find, what we're after is this. Is that what we want? Yeah. Okay, so we want to, the pKa is equal to the negative log of 1.70 times 10 to the minus 5. And this is 4.7. Let me verify that. So that's just from the table. Ooh, no, it's not. That's not even close. It's 4.77. Okay. Yeah. Okay. So, everyone should have this value. So what you need to do is find these numbers and put them in there, and then see what your pH is. Well, that sucks because I made up that 4.92 based off of 4.7. Okay, so my values are not going to be great. Yeah. On what?
So your 50 mLs of that many. So that's technically coming from like the volume and the pH, right?
Yeah. So in the beaker, you put 50 mils of the acetic acid. This concentration is what you found from your previous lab. So you have to make sure that you know what you know how after you did the titrations, you determined what the concentration of the acid was.
Like lab 5.
Yeah.
Or lab 5, 6.
Was it lab 4 that we? Lab 4 is where we found the concentrations.
Okay.
Yeah. So you can use those. If you have trouble, you can't find it, you can use just 0.1. That's fine.
Okay.
But whatever you had for lab 4.
Okay.
So my 0.098 and 0.097 is probably close to what most people have. I just made those up. Okay. So what we're going to do, the reaction is this, that the acetic acid plus the NaOH, it goes just to the right because this is a strong base. It's completely neutralized. The important point here is that it's 1 to 1. So if we figure out the moles of the acetic acid, we know the moles of NaOH. So they're directly related. Or we can I'll show you when we get to that calculation. Okay. So we got to figure out, so what I said in my experiment, I had 50 mils of this concentration of acetic acid, so we're going to multiply these together to find the moles. And then to get to this pH, I had to use 32 mils of my solution here. So I got to figure out moles here. And then so we're going to have a larger number of moles of this, a smaller amount of this, subtract them. And in the process make up our salt, which is a salt solution problem that we did many times. All right, so first thing is, let's do it here. So we're going to do 0.05 liters. Let's see how much. What I want to do is find the moles of the acetic acid that was in the beaker. So this came out to be 0.0049 moles of acetic acid. So that's what we started with. So yours will be probably pretty close. What I pretended to do in the lab was that 32 mils of the sodium hydroxide was added. The concentration was this. And by adding these two together, I created that pH. So this is 0.0031. Okay. So those are this was in the beaker, this was that came out of the burette, they mixed together. So what this is then, we can write an ice table if you want. You don't have to, I'm just showing you, then I'll just show you the math here. But we're saying that we had this, we're mixing, so remember anytime we mix anything we have to change to moles. Because we're diluting each in turn, so that's too complex to try to do as concentrations. This is a strong base, so all of it's being used up. we're creating this, which is really just C2H3O2 minus. So all of this is gone. We've created this much of the base. That's what it is. And then this one here, I claimed it was 0.0818. Let's see if that's right. So 0.0018 moles. So after I added in the sodium hydroxide, here's what we have. And so this, once we change back to concentration, will go here. And this one, once we change back to concentration, goes here. As an aside, you don't actually have to do that because you're dividing by the same number, but I'm going to just do it out of habit. So the concentration of the acid, is going to be, after the fact, after we did the reaction, it's going to be 0.00, and this is going to be divided by our new volume, which is 0.082 liters. The concentration of the base is going to be 0.0031 molar over 0.082 liters. Okay. So we end up with 0. So your numbers will be different, but probably fairly close. That logarithm really kind of takes the edge off of things, so we don't get these gigantic differences. But all right, so my pH, theoretical pH, which I'm trying to see if it will match that, is 4.77 plus the log of the base over the acid. So 0.0387 log plus 4.77. So I get 5.01. Whoa! Serves me right for not noticing that because I had a 0 there. That's why I picked this number to be as high as it is. But we'll go with it. No problem. I'm just a lot further off than I thought it'd be. Okay, so this is what and it's not that bad, but this is what the pH meter says. And this is what I gauge it should be. So this is what it actually should be, assuming you did everything else, you measured these right. And then that would just show the pH meters off. As far as the percent difference, what you do, we always assume that the theoretical model is correct. So what you do is you take, just remember it's absolute value. I could have gotten rid of the negative by flipping these, but always take the absolute value divided by what is supposed to be the correct value times 100%. I'll see what we come up with. Probably pretty outrageous. Yeah, not too bad, actually. No, that can't be right. Hold on. It's got to be worse than that. No, okay. So that I'm at 1.8% difference. All right. I'll accept that. That's not a problem. So, and whatever it is, if you're 30 or 40 or 200, doesn't matter. Just do the calculation correctly. But my guess, these numbers I've seen over the years, they go pretty well. Yeah.
Where did you get that 1.70 times 10 to the negative 5?
Oh, this is Ka. So just tabulated. In one of the labs, you found it yourself. You can use that one if you want, but this is the tabulated one. Okay, and then the one for the ammonia works. It's all 1-to-1. So really, the math when you get done from a distance, it's going to look the same. You're just changing out the numbers. So I'll leave that one for you. You can certainly work with me on that one afterwards. Okay, but going along with this is also the water. We wanted to calculate how much sodium hydroxide should we add to pure water to make it your pH. So mine again, the pH meter showed 11.4. I can see I had it as 11.2 and I changed it to 11.4, so when I did this calculation I found that it looked better if it was 11.4. Well, whatever you had. Okay, so so you found that, what do we have here? So volume added was, oh, actually no, so I think this should be 11.2. Okay, so the volume added is 1.2 mils. That's how much I added to get the pH meter to show 11.2. So now I'm going to calculate it theoretically and see if it comes up to be pH of 11.2. All right, so what you do, you take 0.0012 liters times the concentration of the base. Really bad job there, sodium hydroxide. And this is going to be 0.001 liters. So this is going to give the moles of NaOH, and then I'm going to divide by the new volume, which is going to be 51.2 mils. So whatever amount that you had, it should have been pretty small. That's what I mostly saw. Some people had less than a mil. Some had 2 mils or so. So whatever it is there. So 0.097 times 0.0012. This is 1.16 times 10 to the minus 4 moles of OH minus. So if we know that we divide by the new volume, which didn't change very much, and then we take the negative log, that gives us POH, and then we can find pH. So take your concentration of your NaOH, multiply by the amount of sodium hydroxide you added to pure water. So it should have been fairly small. The concentration of OH minus how much water did you have in that beaker? 50. And I had 50 plus the 1, so total volume, that's going to be 50 plus 1.02, so that's going to be 51.2. So that's going to be 0.051 liters. So I'll put this in here. So 1.16 times 10 to the minus 4 divided by 0.0512. And I get 0.00227 molar OH minus. And then if you take the negative log of this, that's going to give you POH, but we want pH because there's a pH meter that we use, not a POH meter. Or POH, yeah. I suppose they have them, but I've never seen those. So this is 2.64, and so my pH is going to be 14 minus 2.64. 14 minus 2.64, and I get 11.4. Boom! We'll go with you can say that it's 3.6. How about that? Hardly trying at all. I was eating a sandwich at the time when I did this. It was easy. So yeah. It was 2. Okay, good. So I did change it. Good. All right. So we'll just go with 11.4. I thought that was 11.4 up there. But what you do for your percent change is that you do 11.4 minus 11.2. And again, if you switch these around, just take the positive value. It's the absolute value. Divided by a theoretical, which is 11.4 times 100%. But again, whatever you get. If you get a percentage that's 75, 80, no big deal. Just do the math correctly. That's what I'll be looking for. It's very easy to tell when I look at it, if everything went well. And somehow managed to get almost the same amount. Yeah, that's a 10 out of 10. But yeah, whatever it is, don't worry about the percent. What I want you to do is make sure that you got the math right, that you did it right. So don't worry if you do end up with like 300%, you can email me, send me a picture of the work, and let me verify it and see what's going on. But it's most of the time these come up with less percentage, 20% or less is very, very common. And then the ammonia one and the HCl works the same way. I mean, HCl, if you did it out, this would be volume of HCl, concentration of HCl, whatever this is, divided by your volume. And that in that case, for the HCl, you just take the negative log and your pH is that. So it actually is easier. Give that a go. So if you have any questions, come on up. Otherwise, help you out with whatever you need. Otherwise, you can head on out. Enjoy the sun. I think the sun's out. Well, it's breaking through the clouds. We got that. That's all we get.
You said 4.77 is for everyone, right?
Yeah. 1.7 times 10 to the minus 5 is the Ka that you can use. But you might want to take the negative log of it, just check, because I thought it was 4.70 until I walked in here, but I think it's 4.77. Hey, how you doing?
Good luck with today's lesson.